we're going to talk about building fully decentralized anonymous payment schemes for Bitcoin-shaped protocols. So first, we're going to go over the Bitcoin transaction structure and what a UTXO even is. We're going to talk about the properties we would want of an idealized blockchain, both in terms of confidentiality and privacy, as well as integrity. And then we're going to put everything together and build a private and decentralized UTXO-based protocol. So we build applications on top of a cryptographic protocol, which is in turn built using specific cryptographic primitives. So the protocol is kind of like a recipe. So we're baking a cake and we're going to need some sugar for our cake, but we're not going to go into great detail on how to make the sugar. We're just going to get it from the store. And similarly, we're building a cryptographic protocol, and at points we're going to need cryptographic constructions that satisfy some specific properties. But in general, we're not going to go into great detail about how to build that cryptographic primitive. So we're going to focus in this middle tier, and we're going to use some things from the lower tier, the primitive tier. So first, some motivation. So why do people care about decentralized anonymous payment schemes? And that's because Bitcoin is Twitter for your bank account. So the reason people like Bitcoin, it is non-custodial, it is fully decentralized. I don't need to trust that a single node or a small subset of nodes is behaving honestly, and that's a wonderful thing. So we want to keep those properties. Now, while Bitcoin is pseudo-anonymous, in practice, firms like Chainalysis and others make a business out of de-anonymizing Bitcoin users. So there's a multi-million-dollar business working for the US government to identify users of interest. And they are using the fact that a passive observer looking at the Bitcoin blockchain can see the plain text values of inputs and outputs on the chain, and we'll talk about what those are in a second, as well as pseudo-anonymous sender and recipient identities, concretely the hash of each of their ECDSA public keys. So a passive observer, such as a firm like Chainalysis, can use this information, the values and the transaction graph of money flows, to de-anonymize users. And that's true of most blockchains, true of Ethereum. So that's the problem we want to solve. So obviously, one of the properties that people like about Bitcoin is this lack of trust. So we can use a centralized privacy solution or a custodial mixing service and get better privacy, but then we have the risk of the single point of failure running away with those funds. So let's first begin by enumerating the properties that we would ideally want from a cryptographic protocol standpoint. So first, we need it to be private. So we don't want a passive observer to learn anything about values, sender or recipient identities. So in literature, this is ledger indistinguishability. And in terms of integrity, we want some basic stuff. We don't want to be able to spend other people's coins. We don't want to be able to spend coins that don't exist. There should not be double spends. And we shouldn't be able to create or destroy value. Value should be conserved in the system. Okay, keeping aside like things like the block reward. Okay, so that's kind of what we want. So now let's look at how a Bitcoin transaction works, at least the parts that we care about. So on the left, we have a list of I inputs, and on the right, a list of J outputs in a single transaction. So each output has a value associated with it, V1, and so forth. And they each have a recipient, R1, and so forth. So technically, this is a specification in Bitcoin script, but in the simple payments case, it's specifying, just, hey, here's the public key of the recipient, and they need to present a valid signature to spend this particular output. The inputs are going to each reference a previous unspent transaction output, a UTXO, and they're going to unlock that output. So typically they're going to present a signature, which is this sigma sub 1, that can be verified using the public key specified in that UTXO. So pretty easy. Now let's take a look back at the system properties and remind ourselves how we maintain the invariance we just described given the structure of this transaction. So let's think about Bitcoin. So we already established we don't have the first property. We don't have privacy, but we certainly have the others. So how do we preserve the others? So first, when we spend a coin, we include a digital signature, right, signed with our private key. And that signature is a bit of data that lets anyone in possession of the public key verify that this is indeed my coin. And so nodes will reject an attempt to spend a coin that you don't have authorization to spend. Okay. Each input must refer to a valid UTXO. So we can just scan through and check as a node, okay, this references a UTXO that does indeed exist. Each UTXO can only be claimed once, so that's something that since all the UTXOs are in the clear, I can just make sure to check when I verify transactions as a node. And we can't create or destroy value while values are in the clear. So we can just calculate the sum of the inputs equals the sum of the outputs. And of course, this is modulo fees. Okay, so what's the problem? Seems pretty straightforward. So how could we do this maintaining privacy? Well, let's first make the values private by storing them in a UTXO-like thing we're going to call a note. And let's just encrypt the notes, right? That's how we get privacy, we encrypt. The problem is we also need each one of these integrity properties to also be satisfied. So if I just naively encrypt the notes, oh, that solves all our problems. What happens? Well, we definitely need a way to authorize the spending of coins. So we need digital signatures or something similar somewhere. But we kind of have a problem because doing digital signatures like Bitcoin introduces a privacy issue. If I want to find out what my friend Jim is doing on the blockchain, well, I've got his public key because it's public. So I can trial verify each spend, and if they verify I've identified Jim's spends, that violates the privacy property. We're not supposed to be able to learn anything about Jim's behavior. The next two properties, not making up coins and not spending coins twice, well, we've got a problem there too, because we just established we don't have access to the transaction graph, so we can't have nodes check references to UTXOs in the transaction graph. So we can't check those. And checking the value balance in a transaction, the values are encrypted, so we can't just directly sum them like we were doing before. So spoiler alert, in the rest of this video, I'm basically going to describe a slightly simplified view of Zcash Sapling, which is a protocol developed by Zcash, which was originally based on a fork of the Bitcoin code base, which adds privacy. And three great sources of further information about this is the top paper, Zero Coin, was the first paper that succeeded in creating a decentralized system that unlinked transaction origin from sender. It did that with fixed size coins, and it revealed some information, namely the recipient and amounts on chain. It also had big proofs that were too slow to verify, but this was an important paper in the history of this topic. And then Zero Cash, which is a follow-up paper, which improved on the scheme, introduced in Zero Coin, introduced basically what we describe here, a decentralized anonymous payment scheme wherein everything is hidden, sender, recipient, amount. And that scheme also allowed for variable amounts. And with some changes, that was ultimately turned into Zcash. There's been several iterations of the Zcash protocols, and roughly what's described here is Sapling. But these are three great sources. The Zcash folks have a really good protocol specification if you want great detail about all of this. To talk about decentralized payment schemes, we are going to need a primitive that is less common, which are zero knowledge proofs. And basically the idea is you demonstrate a statement. So here, phi of W is true, without revealing anything more about W other than the statement. So W is often called the witness, and that is the private stuff. So it could be multiple variables. You can also provide public inputs if you want as variables to your statement. And the key thing is you can prove honest computation without revealing the inputs. So it is a very powerful thing. So to get a little bit of intuition, we imagine a two-party setting in which we have one person, the prover, and he wants to convince the other party, the verifier, that a statement is true. And they might do some exchange of messages in this interactive setting. So maybe the verifier generates some random challenges, sends them to the prover generates little bits of a proof, and maybe this goes on for quite some time, and at the end the verifier decides, based on the responses that the prover provides, whether or not they should accept. So the key properties that we want from zero knowledge proofs are first completeness. So an honest prover should be able to convince an honest verifier that the statement is indeed true. Soundness, there shouldn't really be a way to trick the verifier into accepting my proof if I don't have a true statement. And zero knowledgeness, the verifier shouldn't learn anything about my witness values, the W values, and that's because those are going to be things like secret keys. So here phi might also be called the predicate. So here's a simple example, which I've seen in a number of settings that I like to give you a sense of computational zero knowledge. So let's have a setting in which imagine your friend, the verifier, is colorblind and you are the prover, and you have two billiard balls, one red, one green, but otherwise completely identical. Now, to your friend, the verifier, they are completely identical, and he doesn't believe that they are actually distinguishable. And you want to prove to him that they are, in fact, differently colored. On the other hand, you do not want him to learn which is red and which is green. So you give the billiard balls to your friend, and he's holding one in each hand. You can see the balls at this point, but you don't tell him which is which. And your friend then takes both balls and puts them behind his back, and he either switches the balls between his hands or leaves them be. So he's making that choice. And finally, he brings them out from behind his back, and you have to tell him whether or not he switched the balls. So you can look at the colors, right? So you can, of course, say with certainty whether or not he switched them. On the other hand, if they were the same color and hence indistinguishable, there's no way you could guess correctly with probability higher than 1/2. So he can just toss a coin and switch the balls if they're heads, and then ask you, did I switch? And then you reply yes, no. Now, maybe you do this once correctly and he's not convinced. He thinks you got lucky. So he can just keep doing it until your friend is convinced. So once you do it enough times, your friend is going to become convinced that the balls are indeed differently colored. Otherwise, the probability that you would have succeeded in identifying all of the switch/non-switches would be very low. And furthermore, the proof is zero knowledge because your friend never learns which ball is green and which is red. Indeed, he gains no knowledge about how to distinguish the balls. So that's obviously a very simplified example, but I think it's a nice one. And that was a very interactive setting. So there's various ways to take an interactive protocol like this and convert it into a non-interactive setting like this. So if you've heard Fiat Shamir, that's one way to do that transformation. The non-interactive setting is a lot nicer because then you don't need to have this extended back and forth. You can publish a single artifact that can be verified by anyone such that it's publicly verifiable. So the prover runs an algorithm called prove that has baked into it the statement phi, the predicate, the witness values, and maybe some other things as well, maybe some public inputs. And that generates this pi, the proof, and they send the proof to the verifier. And the verifier has another algorithm called verify which takes the predicate, maybe some other data depending on the proof system, and then returns whether or not he accepts or rejects. So one of the evolutions of zero-knowledge proofs are zk-SNARKs. So there's a ton of different types of proof systems. This is kind of one of the most popular families of proof systems. So it stands for zero-knowledge succinct non-interactive arguments of knowledge. So the succinctness part just means that the proof size is very small and the verification time is very fast, ideally independent of the size of the complexity of the statement being proved. So we have, for a pre-processing SNARK, we have this additional stage, this additional algorithm called the pre-processing or setup. So given the statements that we want to prove, phi, we need to produce some public parameters that we're going to use for proving and verification. So this is, if you've heard of the Zcash trusted setup that generated toxic waste that had to be thrown away, that's this. And then when we generate proofs, we're going to need those public parameters to produce a proof. And we'll also need them again when we verify. Given a proof and the public parameters, we're going to decide whether to accept or reject. So that's something that all parties in the system need to have, but it doesn't change unless we change the statements that we need to prove. So what we do when we create zk-SNARKs is we represent the computation that we want to prove in a way that the proof system understands. So in our proof logic, we'll write down, so that's in this dotted box, public input, so the data that we are fine with being public on the blockchain. Could be like hash values, things like that. The witnesses, the stuff that we want to be private, so that might be a variable like somebody's private key. And then we have some statements. So what do we actually want to check about these variables? So an example would be a prover saying, I want to convince the verifier I know the pre-image W given hash output hash of W. So W is the private input, the witness, and then hash output would be the public input in that circuit. And then in the proof statements, we would need to write out how to compute that hash. So in practice, what you do is on the programming side is you need to write down that computation. So what's happening in that hash function as an arithmetic circuit. So it's a fundamentally different programming paradigm that's more similar to circuit programming, hence the name. So in this different paradigm, you'll have gates in this circuit that represent simple arithmetic operations, addition, multiplication. And then you'll have A, B, or C represent constants or inputs. And then in this example, you can see that A and B are both inputs to an addition gate. And then the output of that addition gate, so A plus B, is then multiplied by C. So that's the basic idea of how to do SNARK programming. And we're going to need that to satisfy our integrity properties in the presence of our new private notes. So first, let's just recap what we said about how to achieve privacy, and that is value in the system is carried by notes. So notes are going to be encrypted and posted on chain. So we're going to encrypt them to a recipient, and then we're going to send that up to the chain. So inside the note plaintext is all the stuff that we wanted to keep private. So who the note's going to, the recipient, the value that's being transacted, so 1 ZEC or whatever. And then we're going to need a little bit of randomness that we'll talk about later called a blinding factor. So each note is only going to be used once. And when you spend a note, it's no longer spendable. You release the value of that note when you spend it into the transaction that it's spent in, and then you can use that to mint other notes. So they're one-time spends. Now, another feature of Zcash style cryptocurrencies is that there is a separation in the key hierarchy. So this is a very simplified key hierarchy. There's many other keys in the protocol. But I've put in this just to show that their spending and viewing capabilities are separated. So you have a spend key here, SK, which does what's on the tin, lets you spend the coins. And then you have a couple of viewing keys, but here the incoming viewing key, which lets you decrypt the coins that are sent to you. So you can provide that to a third party if you want. That obviously has implications for your privacy. So let's now take a look at what our shielded, our private transactions are going to look like. So there's two types of actions that we're going to discuss in this talk, and those are spends and outputs. So we're going to do a little renaming such that the nomenclature is aligned. So what was previously an input is now going to be called a spend. So an output is just creating a new note, encrypting it to a recipient, and posting it to the chain, and that's basically the output. So we know so far that one of the things that's going in the output are these note ciphertexts, again, encrypted to the recipient. The recipient is going to scan the chain, basically trial decrypt every note ciphertext using the incoming viewing key. And those notes that decrypt, they know, aha, those are notes that are for me. So that's the first piece. So bam, we've got the privacy part tackled, but now we need to figure out the hard stuff, which are all the integrity properties. So next is, how are we going to make sure that we only spend coins that exist in the system? So we haven't actually talked yet about what the nodes are doing here and how that's different from Bitcoin. So we need nodes to keep track of privately all nodes that exist in the system, so they know whether a node exists and whether the node has been spent yet. And the tricky part is we need to do this tracking in such a way that you can't map items in data structure 1, all nodes in the system, to items in data structure 2, all nodes that have been spent in the system, because that's basically the transaction graph. Making sure there isn't a mapping between thing 1 and thing 2 in the transaction graph is the whole point of what we're trying to do here. So we are going to do the following. We're going to derive a quantity from each note that binds us to the value and recipient, so we can't change it later. We can't say, oh, my 1 Bitcoin note was actually a 5 Bitcoin note. And it also needs to hide the value and recipient such that we maintain our privacy requirement. So what we're going to do is we're going to derive a note commitment from every note and store those on each node. Okay, so what is a commitment scheme? So a commitment scheme is fancy cryptography talk for an envelope. So the basic idea is I can't change my value once it's sealed inside the envelope. So if I generate a commitment from a particular value, say 1 Bitcoin, it's infeasible to find a second value that opens to the same commitment. So I later can't come along and say, it wasn't 1, it was 5. Okay, so that's our binding property. I can't change my value once it's sealed in the envelope. And we also have our hiding property. So no one else can look at the value because it's inside the sealed envelope. So it's infeasible, given the commitment, to go back and calculate the value inside. So those are the two properties we get from a cryptographic commitment scheme. The basic algorithms of a commitment scheme are commit and reveal. So to calculate the commitment, we're going to use the commit algorithm that takes a value m and some randomness. So the randomness is another secret value, but one that's picked randomly, hence the name. And then the result, cm, is what will send or broadcast. So cm is the sealed envelope. And then to verify, we, when we're ready to open the commitment, anyone can take m, the value, the commitment, cm, the envelope, and if they have the randomness, then they can check that verifies. So that's verifying an opening of that commitment. Okay, so m, remember m is the message or value inside. So now we know another part of the picture, which is we have our note ciphertext so far in the output, and we're going to add the note commitment, CM1 to CM sub j. So the commitment here, remember, is binding us to the value, the recipient. So we later cannot claim, oh, hey, it was actually, 100 or whatever Bitcoin. And the nodes are, if the transaction is valid, going to add that to a data structure that keeps track of every single note in the system. And for good measure, we're going to need a little zero knowledge proof here, the first zero knowledge proof in the system. And that proof is going to demonstrate that the note commitment is well formed. So it's going to demonstrate that I know the randomness or the blinding factor that was used. So here we'll denote in the dotted line with the pi when we're doing stuff in a zero knowledge proof. So here the public inputs will be the note commitment. Remember that we're putting that publicly on the transaction, so we can use that. There's some other stuff in practice. The private witness values. So here it's going to be the value, the address, and the blinding factor is the bit of randomness that we put in that note. And we wondered why at the time, but that's used for the note commitment. And the statement is just going to be, okay, the note commitment is well formed. So essentially, when I commute the commit algorithm, given these private witness values, I get the public input note commitment. So the real output ZKP is more complex. We'll add a few more pieces in this talk. So then we end up with the following. We've got the nodes keeping track of all note commitments in the system. So how do we do that? So we could just store a big old list, right? So CM sub 1, CM sub 2, so on and so forth until all n note commitments in the system. When we spend, we need a way to demonstrate that our note commitment that we know the opening of is in this set. So naively, we want to prove this set disjunction shown here, and all that's saying is that we want to demonstrate that the commitment is in the first position, or it's in the second position, or ... it's in the last position in the list. So that is a proof that scales with the number of note commitments in the system. So that's not something that we are going to be efficiently doing. So we need to think a bit more about this data structure. Maybe we don't use a list. So in fact, what we do is we use a Merkle tree. So nodes, instead of maintaining a list, maintain an incremental Merkle tree containing all note commitments that have ever existed in the system. These Merkle trees must be append only because modifying or deleting entries would leak information. So a Merkle tree is just a tree, a data structure where internal nodes are the hashes of their children. So for sapling style shielded pools, each leaf in the tree stores a note commitment. So the tree is very large for sapling, so it's depth 32 tree. And one of the great properties of a Merkle tree is it compresses a very large amount of data into a small fixed-sized value, and that is the root or anchor of the tree. So what are we going to do with these commitments? So we're going to store them in the leaves and do Merkle proofs to demonstrate our note is in the system. So that gives us an easy way to prove set ownership via a path that's provided. So it consists of the note. So here, let's say the red leaf is the note that we want to spend. So we're going to provide in our proof the siblings. And if our note is truly in the tree, when we as the verifier hash together the note commitment and its siblings and so on and so forth up to the root of the tree, we should agree on the root that we see. How do we make this private? Well, we do all of this Merkle path verification in zero knowledge. So we do it inside the circuit. And the reason for that is otherwise we would be revealing which note we're spending. So the public input of the proof would be the anchor of the Merkle tree. And that's something the verifier would provide because it's keeping track on its side of all of the note commitments in the tree. And then the witnesses would be the note commitment. which as we've just described should be private, and its siblings in the tree, because we also want that to be private because that reveals which note commitment we're spending. We're going to add a proof to each spend. So that's shown on the left side. Okay, so using what we've shown so far, we've shown how we maintain privacy while only spending coins, i.e. notes that exist in the system. So next, nodes are also going to store another data structure, the set of all nullifiers that have been revealed. And so this is just going to be a set, nothing particularly fancy. When we do a spend, we're going to reveal the nullifier associated with the node. So that's NF sub A and NF sub B and so on. Once revealed, you cannot spend the same note again. So nodes will check that the nullifier has not been revealed in a previous transaction or elsewhere in this transaction. And there can only be one valid nullifier per note. So spends reveal a nullifier. It's like a serial number associated with a note in the system, but doesn't link to which one. And there's a one-to-one mapping between notes and nullifiers, although that is not public. So once revealed, that same note is considered invalid in future spends. So now on our spend, we have a nullifier, the serial number that is revealed, and a spend zero knowledge proof. Okay, so let's take a look at what's in our spend zero knowledge proof so far. So we've got, on our public inputs, we've got the root of the Merkle tree, we've got the nullifier. In our private witnesses, we've got the plain text values that go in the node, so the value being spent and the address, so the recipient. The Merkle proof are the siblings in the tree, and the note commitment we can calculate from the value, address, and blinding factor, which isn't written here, but also would be a private witness. And then the statements are check the Merkle proof. So the Merkle proof demonstrates the note commitment exists in the tree with the provided public anchor. So the provided public anchor we're checking against the public input anchor that the verifier provides. And we'll check the nullifier is correctly derived. Okay, so that gives us the state that the nodes need to maintain. So they need, on the left, they need a Merkle tree of all note commitments that exist in the system. These commitments live forever. And on the right, we have the nullifier set, which corresponds to all spent notes in the system, but in such a way that it does not reveal which notes are spent. So you can't map between these two data structures. Okay, so with that, we've got our integrity properties of not spending coins that don't exist in the system, not being able to spend coins twice, and we did it while maintaining privacy. So we have two more integrity properties to check, but we need another cryptographic primitive to be introduced at this stage, and that is a re-randomizable signature. Remember why we can't use regular signature schemes in these protocols, and that's because you can take a target public key and do trial verification of the signatures associated with a particular transaction or a set of transactions to figure out if this target did indeed do that spend. So trivially linked spends. Instead, what we're going to do is we're going to derive a randomized key, RK, from our real key that we're using for signing, AK, and we're going to use that instead to do our signatures. So we're going to calculate RK from the real key plus some randomizing factor alpha times a point. So we're going to need to demonstrate inside our proofs that the randomized key, which is public on the transaction, is a correct randomization given the witnessed real key, AK, which we keep private, and the randomizer alpha, which we'll also keep private, and then B is just something that we'll set. So now we're going to provide a digital signature, sigma, and we're also going to provide RK, the randomized key that was used to create that signature. So it's a bit clever in that we're modifying the public key every single time we spend a coin in such a way that the public keys cannot be linked. So this is the re-randomizable signature scheme. So we got now in our spend far left, nullifier, spend zero knowledge proof, signature, and the randomized verification key. So now we're going to add a few more things to our spend ZKP. We're going to add a public input, which is our randomized key, public key, RK. We're also going to witness the key that we would have otherwise used that would have linked the spend, so spend authorization key, that was AK. And we're going to witness the randomizer alpha. And then we're going to add a little statement in our spend ZKP that just checks the equation that was on the previous slide. So it's going to check that the randomized spend verification key is correctly derived from our witness values. So that's it. Have a way of showing that we can't spend other people's coins using digital signatures, just re-randomizable ones. So finally, we need a way to check for each transaction that we're not creating or destroying value. So let's go back to the commitment schemes for a moment. So recall earlier in the talk, we talked about these two phases, commit and reveal, which let us verify the commitment. We're now going to show a concrete instantiation of a commitment scheme, which is Pedersen commitment. So basically, the commit algorithm is taking the value m or message m, multiplying it by a fixed point g, and then adding in some randomness or blinding factor times another fixed point h. And we just recompute that when we do the reveal and check that it equals the commitment that was provided. So those that are familiar with elliptic curve cryptography obviously know what's happening here, but I didn't go into those details, but I have another video on that if one is interested. Pedersen commitment scheme has this property that we're going to use called additive homomorphism. So a homomorphism is just a function between two algebraic structures that preserves an operation. So it keeps the structure's properties intact when applied. An additive homomorphism is a type of homomorphism that specifically preserves addition. So applying the function to the sum of two elements is the same as adding the function's values for each element individually. So that said in words is a bit confusing, so we'll show it in math. So we want to show Pedersen commitments are additively homomorphic. So we're going to take two example commitments to see this property. So first, we've got commitment 1, so we're going to just write out the definition of the commit algorithm given our value or message 1 and the first blinding factor, randomness of 1, and just plugging in the equation we saw in the previous slide where we multiply each in turn by random points g and h. That's what the first commitment is. And the second commitment is the exact same thing, just with a different subscript. So not that crazy. The addition of the first commitment and the second commitment is, let's write it out. So we have m sub 1 times g and randomness 1 times h plus the second message times g and the second randomness times h. So let's rearrange those a little bit, group the terms that are multiplied by g together, group the terms that are multiplied by h together, and we can see, looking up at the definition of the commit algorithm, that that's just the commitment of the additions. So that is demonstrating our property of additive homomorphism. So why is that so cool? And it's cool because that's going to give us a way to verify the value balance of the transaction. So for every action in the transaction, we're going to add a commitment to the value. The value is going to be replaced with m. So our value commitment is going to be v times our point g plus random blinding factor times h. And this is a different blinding factor from the one that was in the note commitment. So the spends are going to be positive. So that's releasing value into the transactions. And the outputs are going to be negative. So they're consuming values from the transaction. So that is the convention we're going to use, and if all goes well, we should have a commitment to a 0 value when we add the value commitments in the transaction. So let's go to our big picture and add in those value commitments. So now associated with every spend, we've got some value commitments. And what we're going to do is we're going to sum over all the i's and the j's for all the different value commitments and verify that it is a commitment to 0. So the part that we also need is the sum of the random blinding factors. So we'll provide that as well on the transactions, the sum, not the individual ones, such that we can check this. And that is how we check the value balance. So this is how we verify all of the integrity properties while maintaining privacy. So in summary, this is how one can do decentralized anonymous payments. So all state in the form of notes is encrypted. The chain never sees the recipient, sender, or value. We have a note commitment tree that maintains an append-only data store of all state in the system, so every note. Spends of a note must demonstrate in zero knowledge the note commitment is in the commitment tree. State gets deleted by revealing a nullifier only once. That goes into the nullifier set. Observers cannot link the nullifier to notes or state that has been invalidated. Spends must demonstrate control over the note via a randomized signature. And then value conservation is provided through the additively homomorphic property of value commitments. So that is how decentralized anonymous payments work. I hope this was useful, and thank you for watching.